And our next presenter is Sophie from Tallinn University of Technology. And the title of the talk is Perspective of Phosphorite Deposits as Rare Earth Resources.
So, short people problem. So, I hope not everyone is already asleep. A last talk still on phosphorite, following the one of Laurie, this time for focusing on rare earth potential in Estonian phosphorite, which has been the topic of my PhD so far. So, how does it work? Okay. So we talk already a lot about rare earth today. So they comprise 15 lanthanide, yttrium, and scandium. They find wide use in the industry. It began with cerium oxide used as polishing tools, and then they become quite critical with the development of neodymium magnets starting from the 80s, which are found in numerous electronics component and wind turbine for green technologies. As we all know, the situation of Europe in terms of sourcing is pretty bad because we produce none of them. Here on the right, you have kind of overview of the current state of rare earth production, which is uh, largely led by China and also other Asian countries which produce rare earth but refine them in China. So, because of this supply question and depletion of high quality deposits, there's a rising interest in what we call unconventional deposit or resource, and one of them are the phosphorites. If we go a bit deeper in the topic of rare earth elements, so we have all this group of lanthanum to lutetium, adding with it ytterbium, and they are considered all together because they share similar chemical and physical properties. They are lithophile elements. They have a large unique radius, so approximately 1 angstrom, 3 plus oxidation state, aside from cerium and europium, which are often used for investigating redox condition, and their electronegativity is quite close to calcium, sodium, and strontium, and this is why they are often found as substitution of this element. So from light rare earth, so from lanthanum to lutetium, the properties of this element vary progressively. There is a progressive filling of the four orbital orbites, which induce variation in the property. So a decrease of the unique radius, increase in electronegativity, and this affects the partitioning of rare earth in natural environment. That's why you will find the light rare earth, mainly lanthanum and cerium, in higher proportion, and the heavy rare earth in below trace amount, often below 1 ppm. So they are common elements, but yet they are not found in mineable condition. In other groups, their abundance is above copper, but as they have specific properties, they don't fit in most mineral structure. That's why we don't find them so much in silicate. And the main mineral, as it was very nicely introduced by Oli earlier, are commonly bastnaesites and monazite, well, which contain mostly lanthanum and cerium. They are found in carbonatites mostly. And another main rare earth mineral in terms of mining is xenotype, yttrium phosphate. So those three minerals are the most commonly exploited. And the one that will interest us is apatites, which is why I consider personally as a trash can of mineral because it can accommodate almost everything in its calcium site. And this will be our main focus later on. But if we continue a bit on the availability of rare earth on the market, since the production is mainly driven by carbonatite sources, we found mainly mainly, sorry, lanthanum and cerium, and some of the other light rare earth. And the other elements, medium and heavy rare earth, are rather less common. If we consider the graph on the middle, which correspond to average laterite or clay ore, for example, the Liangshan province in China, then we have a bit more of yttrium and other heavy rare earth. But in general, there is a need for alternative sources of this medium and heavy rare earth because these elements are needed for the development of green technologies. So, concerning the alternative sources, there is both the recycling. I mean, it's almost a bad word. No, we should say the valorization of industrial waste, mud rock, waste from mine, magnets, and the raw resource, so unconventional deposits, so coals, ocean bottom sediment, geothermal brine, some black shale, not Estonian one, sadly, and phosphorite, which will be the main focus of my topic. So phosphorites are relatively common deposits. They are mostly formed by upwelling of deep current to the shallow continental shelf. So these currents are rich in soluble element, phosphite, carbonate, rare earth. They are transported up to the surface, and the phosphorite crust will form progressively because those elements are not soluble anymore, they precipitate. The phase that were hosting the rare earth, so mainly in our case manganese and iron oxide, desorbs, and the activity of microbial degradation and organic matter degradation helps to precipitate all this apatite. And initially, this apatite is often of the hydroxyapatite type and has the initial low rare earth content. And the rare earth enrichment occurs during the diagenesis. So, in sedimentary phosphorite, we don't have nice mineral really. It's mostly apatite in the form of concretion, mineralized debris, so for example, fish teeth as a deposit in Kazakhstan, or in the case of Namibia and Estonia, coquina. So it's quite uncommon mineralization to deal with. So there's a lot of things to assess them and investigate. In Estonia, phosphorite are from lower Dovetian formations. They're quite widespread on the country, but we mainly focus in two deposits, Tulsa and Aseri. If we speak on wall rock content, we have approximately in the Tulsa ore and the presented sections 27% of apatite with around 700 ppm of rare earth, and in the lower parts a small horizon extremely enriched where the phosphorite is cemented by carbonate and reach up to 60% of apatite. So, as it was stated before, it's a bit unusual because the mineralization is a fragment of shells of brachiopod. And here is a little example of a drill core from the Aseri deposit, where here the shell fragments are almost completely black and hosted in sandstone. If we get deeper in the characterization of this apatite, it's part of a work we conducted in Oulu University. This Baltic phosphorite behave a bit like placer, so high volume, low grade, at least for rare earth deposit. They are the apatite is autogenic, so that means it's a recrystallization that occurred during the diagenesis, so the shell are being recrystallized. As you can see on the image on the right, we can find some almost decent crystal, and there is an important textural variability. For example, due to the shell textures and different enrichment. For example, here, same image, iron, manganese, strontium, and we were in need of rare earth in situ analysis, both to understand really the in situ distribution or to predict apatite behavior and later on for processing. But one issue, not only with Estonian phosphorite, but all type of sedimentary phosphorite, is that their individual rare earth content is often below the detection limit of conventional automated mineralogy tools, such like CamScan, which is maybe the most famous. So it's very difficult to reach them with EDS or EPMA, and we were a bit stuck until we tried a LACPMS imaging method, which was initially applied for geochronology, but on a resource perspective. I won't go too deep in the technical points, but in few lines, it's work a bit like a raster map where each ablation point are considered as pixel, and then we can use this pixel as base for chemical clustering. Here is an example of, in the middle, a photograph of apatite shell from acerine and carbonate matrix, or we're able to separate them. And after that, we can use an element as a pooling channel to sort our chemistry. So instead of using of classical linear distribution, we use what we call an ECDF, so empirical cumulative distribution. This is quite good because it enhances, I don't know if the laser will work. No, it doesn't, but it will enhance lower and higher value. And we have been investigating enrichment process of this phosphorite and apatite distribution. So we investigated different elements for the behavior of our deposit, but here I will mostly focus on uranium to track the variability of our rare earth signal from the beginning to the late diagenesis. So the first thing here, we have above the ECDF map and then the PRS normalized rare earth value from two deposits, Acerine and Tulsa. And the first thing we initially see is that most of our rare earth data are rather homogeneous. They lay in the tenfold range, but we have variation of diagenetic overprint. For example, in Tulsa, we can reach quite low grade, so below the normalization. This is translated also with very poorly recrystallized apatite. We have almost the texture of the shell. And oppositely in acerine, we have very limited low value and specific enrichment, but I will show in the next slide. And oppositely, as the diagenetic overprint progress, the apatites fill and grow progressively, and we have almost no porosity. So depending of the locality, we have a quite big influence on apatite texture. But as I said, in this acerine deposit, we found a specific enrichment which is mainly located on the edge of the shell. If we doesn't work on the screen. If you look at this image, you can see here it matches very well the uranium enriched zone. This image here is a photograph of the yellow part here. And we reach content up to 121 fold, which is really high. I will give the absolute value later on. And this is extremely high for sedimentary phosphorite. And so far, this also coincides with quite high uranium content. Most of the time, Estonian phosphorite are really poor in uranium, but here we reach to almost 500 ppm. And we so far consider that this specific enrichment is due to specific oxenic setting in the sediment and potentially lithogenic input or foul fluid. Now, with this semi-quantification, we built a compositional model of our apatite. So since we have pixels, we can cluster them and calculate model properly. And we compared variability in Tulsa and acerine. Here, data in yellow are the value of rare earth, absolute value in the edge enriched in uranium and rare earth. And the blue one are rather the main only diagenetic enriched apatite. Main thing to see here is that these edges enriched in rare earth yield the economical value, because in nursery we reach this value, sum of rare earth up to 7,000 ppm, almost 10,000 in some pixels, and our average grade was around 2,000 ppm. In Tulsa, it's a bit less since the enrichment was less pronounced, but on this sample, we still found almost 2,000 ppm on average, and the edge were reached up to 4,000. And this implied that we really need to minimize the fine loss or generating those fine to keep the value of one phosphorate. And to show a map of the same sample, here it's the neodymium LICPMS mapping, and here we have content in yellow reaching of 4,000 ppm of neodymium in this area. So it will be really a critical point to properly recover those fragile weathered parts. Now, if we look at the ore assessment, or one critical point is the individual rare earth distribution within the apatite. Obviously, this is not the only point to consider, cost of processing and efficiency, but we use a method what is called outlook coefficient, so calculation of absolute rare earth content and the ratio of what rare earth are considered as needed for the green transition. We have neodymium, dysprosium, europium, yttrium, and rare earth that we'll consider to be excessive. For example, cerium or lanthanum. And in that case, our deposits, both Tulsa and Assery, lay rather in the same range, so what is considered as promising. The South Russia line corresponds also to the fish deposits fish apatite deposit I was mentioning, and this show a bit that the average rare earth content is quite promising in Estonian phosphorite. This is mainly due because we still have a great part of heavy rare earth and middle rare earth. Yttrium in Tulsa, for example, is around 20%, middle rare earth represent 11%, and neodymium and praseodymium around 20%, both together. Aceri, it's quite similar, just a bit more enriched in heavy rare earth, but otherwise both settings show similar rare earth distribution, which is quite great. Consider other deposit, for example, carbonatite that mostly host light rare earth. So quite promising things to look for. And what are our perspectives so far in conclusion? Well, I think we have different talk enough to show that phosphorite are highly variable deposits, but they tend to homogenize during diagenesis. Phosphorites from Estonia are promising low-grade rare earth ore. We have a very specific, highly enriched fraction on the edge of the shell. And a key point will be to minimize fine loss for maximal recovery. What we plan to do so far, how to reconcile wall rock data and LECPMS data, applied this method to concentrate and other apatite ore, and beneficiation process which will come with the REMUB project that has started this month actually. So thank you.
Thank you. Time for questions.
Thank you very much. Very good presentation. I think maybe this question could be for all those that give the presentation on the phosphorites. Because as you showed in your presentation, the phosphorates is because the world population is increasing and we need more of these to produce fertilizers and all that. So phosphorites or phosphates are very, very important. But then we are also now considering it as a source for rare elements.
Yes, as byproducts.
So the question then is, is it going to be the plan that you can then try to introduce the recovery of rare earth elements as a kind of a side or as a kind of a value chain that you are adding
Yes,
to the already
that's the
existing
point to
phosphate. Is
separate
that the
them
plan?
from phosphorus. Yes.
Okay, so that is the plan here.
Yeah.
Okay, thank you very much then.
Is there anybody else?
Very interesting, Sophie. Thank you. I was just wondering if there is any idea about the timing of these rims around the outside. I know you said that enrichment usually comes during diagenesis. Is there any sort of late stage fluid, hydrothermal fluids that might be sort of circulating through these that might be causing remobilization? And so I know you mentioned the textures. Is there any sort of evidence for what might be going on there?
This is actually a good point and a point I'm working on, because not everywhere, but in this acid deposit, both phosphorite and black shale show sign of influence of some fluid or heterogeneous input. On phosphorite, well, we have this enrichment, we have titanium, almost anatase weird edges, and in black shale we have specific zinc and lead enrichment. Some of our colleagues that has been working on limestone showed possible influence of the caledonite orogenesis, so a bit 10 or 20 million years after. So the idea is later on, after this main diagenesis, we have far field influence, but yet it has to be proven.
Thank you, Sophie.